resistors in series and parallel. Okay, we start with the comparison between series and parallel circuits. Okay, so we have series connection and parallel connection. Okay, we are going to compare current and voltage between series and parallel circuits. So let's start with current. Okay, always think of current as a flow. Okay, so let me show you. Whatever that is flowing from the battery. Okay, so the current coming from the battery will flow through the first resistor and then go out and then will flow through the next resistor and then will go out and then will flow through the next resistor and then will go out and then will flow through the next resistor and then back to the battery. So you can see for a series connection, you don't have a splitting point. You have the same current flowing through resistors. Okay, so if you can think of current as a flow, you are going to see that in a series connection, the current is the same through each resistor in a series connection. Now, for a parallel connection, always think of current as a flow. Now, the current coming from the battery, okay, when the current meets a splitting point, the current is going to split. Okay, the current is going to split. Part of the current will flow on this branch, another part of the current will flow on this branch, another part of the current will flow on this branch, and then the current will join. Now you are going to have 100% of the current. Okay, back to the battery. Okay, so always think of current as a flow. So for a parallel connection, you have a splitting point and then you have a joining point. Now you have 100% of the current back to the battery. Okay, so in a parallel connection, if you can think of current as a flow, you are going to see that current divides among each branch. You have to say among each branch. This is a branch. This is another branch. This is another branch. Okay, you have to say current divides among each branch. Okay, because on one branch you can have more than one resistor. Okay, so we have to say current divides among each branch. Now let's compare the voltage. When the current is the same for a series connection, the voltage is going to divide, okay, the opposite. So voltage divides among each resistor. And for a parallel connection, you have the current divides and the voltage is the same for each branch. In a parallel connection, okay, you have to see this branch, okay, branch. Okay, for a parallel connection, you have voltage is the same for each branch. Okay, because on one branch you can have more than one resistor. So this is why you have to say for each branch. Okay, now for the formula for finding the total resistance in a series connection, this is the formula. Okay, for a series connection, you are going to add, okay, R1 plus R2 plus R3 plus R4 and so on, depending on how many resistors you have in a series connection. Now, for a parallel connection, the total resistance, okay, for a parallel connection, you are going to use this formula, okay, 1 over Rp. Rp for resistance in a parallel connection, you have 1 over R1 plus 1 over R2 plus 1 over R3 and so on, depending on how many resistors you have in a parallel connection. Okay, let's carry on. Now, we are going to see how does current divide in parallel for each branch. Okay, let's see this. You have to see this. Okay, when you have the same resistance on each branch, the current is going to divide equally. Okay, on this branch you have 3 ohms. On this branch you have 3 ohms. When you have the same resistance on each branch, the current is going to divide equally. This is why you have 4.5 amperes through this resistor, and then through this resistor you also have 4.5 amperes. Okay, 4.5 plus 4.5, you are going to have 9 amperes. Okay, you have the 9 amperes, which is dividing. Okay, 9 amperes from the battery divide. Okay, so you have 4.5 through this resistor and then 4.5 through this resistor. Okay, this is what you are reading using an ammeter. Okay, and then 4.5 and 4.5, they are going to join, and then you're going to have 9 amperes again. Okay, so you have, when resistance on each branch is the same, the current is going to divide equally. Okay, let's see another example. Now you have 15 amperes coming from the battery. You're going to have a division. Okay, a division of the current. So you also have to notice on this branch you have 7 ohms. On this branch you have 2 plus 5, which is 7 ohms. On this branch you have 7 ohms. Okay, again you have the same resistance on each branch. Okay, 7 ohms, 7 ohms, and then 7 ohms. Okay, you have a series connection. You know how to calculate for a series connection. Okay, you have R2 plus R3. Okay, 2 plus 5, you're going to have 7. Okay, this is why the 15 amperes is going to divide equally. You have 5 amperes on this branch, 5 amperes on this branch, 5 amperes on this branch, and then they are going to join. You're going to have 15 amperes again back to the battery. Okay, so you can see 5 amperes, 5 amperes, 5 amperes. Okay, when you divide 15 by 3, you're going to have 5 amperes, 5 amperes, 5 amperes. Okay, so when the resistance on each branch is the same, current divides equally. Okay, equally. Now, when the resistance is not the same, okay, 5 ohms and then 10 ohms, the current is not going to divide equally. Okay, so this is what you are going to have. When resistance is not the same on each branch, current divides unequally. Okay, you can see you have 6 amperes and then 3 amperes. Okay, you have 9 amperes coming from the battery and then divide on this branch. Okay, on this resistor you have 6 amperes flowing through this resistor. On this resistor you have 3 amperes flowing through this resistor. Okay, so you're going to have, they are going to join, and then you're going to have again 9 amperes. Okay, 6 plus 3, 9 amperes. Okay, you have a splitting point and then a joining point. Okay, now the larger current flows through the smaller resistor. Okay, this is always the case. And then for the larger resistor, you are going to have a smaller current flowing through the larger resistor. Okay, so this is always the case. Okay, remember, resistance is the same as opposition. Okay, the larger the opposition, the smaller the current that is going to flow through the resistor. Okay, the smaller the opposition, the larger the current that is going to flow through the resistor. Okay, now current divider rule for parallel connection. Okay, so this is a parallel connection. So if you are given the value of each resistor and total current in a parallel connection, how can you find the current through each resistor? You can use these three ways. Okay, you are given a parallel connection, you are only given the value of each resistor. Okay, you are given the value of each resistor, and you are also given the total current. Okay, the total current. The total current is 8 amperes. Okay, you have 8 amperes. The 8 amperes is going to split. Okay, you have 8 amperes, which is your total current. It's going to split and then join, and then you are going to have 8 amperes again. Now, how can you find the current through each resistor? Okay, how can you find I1 and I2? Okay, we are going to use three ways to solve this problem. So this problem is about current divider rule for parallel connection. You have division of current only in the parallel connection. Okay, we are going to see that. So we are going to use three ways to find I1 and I2. Okay, I1, the current through R1. I2, the current through R2. Okay, so the first method, you have to know that the voltage is the same across each branch. Okay, in a parallel connection, the voltage is the same across each branch. So you need to find the voltage across the resistors in a parallel connection, and then you are going to proceed. The voltage is the same across each branch in a parallel connection. So you are going to use this formula. Okay, remember this formula. You are going to need this formula. So find the voltage, because the voltage is the same across each branch in a parallel connection. Okay, so you need this formula. Okay, we know our total current. Okay, 8 amperes, the total current. Okay, you need the total resistance. Okay, you have resistors in parallel. You have to calculate the total resistance. So we are going to use this formula. So this is equal to, you have 1 over 6 plus 1 over 4 equal to 5 over 12. 5 over 12 is equal to 1 over Rp. Rp for resistance in a parallel connection. You need Rp, not 1 over Rp. You need Rp. So Rp is equal to, you are going to flip, okay, 12 over 5. Okay, 12 over 5 ohms. Now you can calculate the voltage, which is the same across each branch for a parallel connection. Okay, so the voltage is equal to the current, 8 amperes, times the resistance, which is 12 over 5. You are going to have 19.2 volts. So you have the same voltage across this branch and the same voltage across this branch. Okay, you have 19.2 across this branch and 19.2 volts across this branch. Okay, So now you can calculate I1 and then I2. So I1 is equal to, you are going to use this formula. Okay, you need the current. You are going to use the same formula. You need the current. So let me show you. You need the current. You have to divide by resistance so that you can cancel and you are going to be left with only the current. So what you do on the right, you also do it on the left. Okay. So now you can cancel R and R. Now, can you see the current is equal to the voltage over the resistance? So I1, which is the current, is equal to the voltage. The voltage is the same across each branch. So you have the voltage over R1. Okay. When you are calculating I1, you need R1. Okay. When you are calculating I2, you need R2. So I1 is equal to the voltage 19.2 over R1. R1 is equal to 6. This is equal to 3.2 amperes. Okay. Now I2 is equal to, use the same formula. Okay. When you are calculating I2, you are going to have I2 is equal to the voltage over R2. So I2 is equal to the voltage over R2. The voltage is the same across each branch in a parallel connection. So I2 is equal to 19.2 over 4. This is equal to 4.8 amperes. Now, another way, use the following formula if you only have two resistors in a parallel connection. You can use the following formula if you only have two, as in this example, you only have two resistors in a parallel connection. So, make use of the following formula. So, I1 is equal to, you have this formula. Okay, this is equal to, you have the total current. Okay, IT, the total current times R2. Okay, R2 over R1 plus R2. Okay, 6 plus 4. This is equal to, you have 8 times 4 over 6 plus 4. This is equal to 3.2 amperes. Okay. Now, I2, you are going to use this formula. Okay. You have the total current, 8 amperes. Okay. Times R1. R1 is equal to 6. Okay. Over R1 plus R2. Okay. 6 plus 4. This is equal to, you are going to have 4.8 amperes. Okay, you can see. Now, you have to notice. Let me show you. When you are calculating I1, you are going to have in the numerator R2. Okay, when you are calculating I2, you are going to have in the numerator R1. Okay, you have to see that. Okay, so we are done with the second method. Now, the third method. Now, the third method, use the following formula if you have two or more than two resistors in a parallel connection. So, this formula can be used if you have two or more than 2 resistors in a parallel connection. Okay, so we can use the following formula for this case, okay, because this formula can be used for 2 resistors in a parallel connection, even 3, 4, 5, and so on. We have 2 resistors. We can use the following formula. So to find I1, okay, you only replace I, okay, I. So let's find I1. I1 is equal to, you have total current, okay, IT, total current 8 amperes times you have 1 over R1, okay, 1 over 6 over 1 over R1 plus 1 over R2, okay, 1 over 6 plus 1 over 4, okay. This is equal to, let's see, you have 8 times 1 over 6 and 1 over 6 plus 1 over 4. You're going to have 3.2 amperes. Okay, 3.2 amperes. Now, I2, you're going to use this formula. Okay, the same formula. Okay, the same formula. Now, you change your I with 2. So, this is equal to 8 times 1 over R2. R2 is equal to 4. Okay, 1 over 4. 1 over 6 plus 1 over 4. This is equal to, okay, you're going to have 4.8 amperes. Okay, 4.8 amperes. Okay, the same answers. Now, you have to notice this. Okay, when you are calculating I1, you are going to have in the numerator 1 over R1. Okay, when you are calculating I2, you are going to have in the numerator 1 over R2. Okay, let's move on. So remember, current division happens only in parallel circuits. Okay, you have division of current only in parallel circuit, not in series circuit. Let's move on. Now, we are going to talk about voltage divider rule for series connection. Okay, you have division of voltage in a series connection. Okay, in a parallel connection, you have division of current. Okay, remember, you are given the following circuit. If you are given the value of each resistor, okay, if you are given the value of each resistor and the total voltage, okay, the total voltage across the resistors in a series connection, how can you find the voltage drop across each resistor? So you can use these 2 ways. Okay, you are given the following circuit. The first one, for a parallel connection, the voltage is the same across each branch. Now, for a series connection, what is constant? The current is the same. Okay, so you are going to find the current in a series connection and proceed. So the current is the same through each resistor in a series connection. Okay, the current is the same through each resistor in a series connection. So again, remember this formula. You are going to use this formula to find the current. So to find the current, you need the current. Okay, you need the current. You have to divide by resistance so that you can cancel, and then you are going to have the current. So what you do on the right, you also do it on the left. Okay. Okay. So can you see? Now you can cancel R and R. Now you have the current is equal to the voltage over the resistance. You need the voltage. You are given the voltage. Okay. 15 volts. You need the resistance. Okay. Calculate the total resistance for a series connection. So resistance for a series connection is equal to R1 plus R2 plus R3. Okay, so this is equal to 2 plus 1.5 plus 4. This is equal to 4 plus 2, 6 plus 1.5, 7.5. So the current is equal to 15 over 7.5. This is equal to 2 amperes. Now you are going to find the voltage drop across each resistor. Okay, you are going to use this formula to find the voltage drop. Okay, you are going to use this formula. Okay, V1 is equal to, you are going to have the current. Okay, the current is the same in a series connection. Okay, times R1. Okay, when you are calculating V1, you need R1. This is equal to I, which is equal to 2 times R1. R1 is equal to 2 ohms. Okay, you are going to have 4 volts. Okay, now V2, this is equal to I times R2. The current is the same. Okay, the current is the same. So this is equal to 2 times R2. R2 is equal to 1.5. You are going to have 3 volts. Now V3 is equal to I times R3. Okay, you're still going to use the same formula. This is equal to, you have the same current. Okay, 2 times R3. R3 is equal to 4. This is equal to 8 volts. Now the second method. Okay, use the following formula. So this is equal to R1 over total resistance. Okay, you have total resistance for a series connection. Okay, total resistance is equal to this. Okay, 7.5. So 7.5 times V, this is V, this is equal to 4 volts. Now V2, you're going to use this formula. Okay, can you see? When you are calculating V1, you're going to have R1 in the numerator. When you are calculating V2, you're going to have R2 in the numerator. So this is equal to, you have R2 over total resistance times V. You are going to have 3 volts. Now V3, okay, when you are calculating V3, you are going to have R3 in the numerator. Okay, so this is equal to R3 over total resistance times V. You're going to have 8 volts. Okay, so again, remember, voltage division happens only in series circuits. Okay, okay, let's solve these two problems. Okay, problem number 1 and problem number 2. Okay, let's start with problem number 1. Okay, solution. So what is the equivalent resistance for the circuit below, okay? In other words, what is the total resistance, okay? The total resistance. You have to see this about this problem, okay? Let me show you. Can you see the three resistors are in series? You can solve this part first, okay? The three resistors are connected in series, okay? So resistance in series is equal to, you're going to have R2 plus R3 plus R4. So this is equal to 3 ohms plus 2 ohms plus 1 ohm. You are going to have 6 ohms. Now, if you want, you can redraw the circuit by replacing these resistors with one resistor, which is equal to 6 ohms. Okay? Now, when you carry on, you have to notice again. Can you see this resistor and this resistor are connected in parallel? Okay? They are connected in parallel. You have to see that. Okay? In parallel, you have a splitting point. Okay? This is the splitting point. And then you have a joining point. Okay? This is the joining point. Okay? Splitting and then joining. So you are going to use this formula. This is equal to 1 over 2 plus 1 over 6. Okay? For parallel connection, you have a parallel connection. So you are going to have 2 over 3. So you need RP, not 1 over RP. Okay, you need RP. RP is equal to, you are going to flip. So you are going to have 3 over 2 is equal to 1.5 ohms. Now you can redraw the circuit by replacing the two resistors which are connected in parallel. So you are going to have this. So now you can see you have a series connection. So total resistance or equivalent resistance is equal to, you have 1 plus 1.5 plus 4. You are going to have 6.5 ohms. Now, problem number 2. Solution for the circuit shown in figure 1. Determine A. The reading on the ammeter. You need to determine the current, okay, going through this resistor, 6 ohms resistor. Okay, you need to determine the current. How can you determine the reading on the ammeter? You have to remember the voltage. Okay, the voltage is the same across each branch for a parallel connection. Okay, V is the same. Okay, V is the same for a parallel connection. So we know the voltage is the same across each branch. Okay, across each branch. You need this formula. You need the current and the resistance. Can you see on this branch, you have enough information to find V, which is the same across each branch. You have enough information on this branch. So let's find V. This is equal to, you have the current 3 times R, which is 5. You are going to have 15 volts. The voltage is 15. Okay, 15 on this branch, and 15 on this branch, and 15 on this branch. So on this branch, we have the voltage and we have the resistance. Okay, we can find the current through the resistor. Okay, so you need current. You are going to use the same formula. You need current. Okay, when you have this formula, okay, to find current, what you can do is to divide by R, okay, so that you can cancel and then you're going to have current. So what you do on the right, you also do it on the left. Now you can cancel. Now you have current is equal to V over R. So current through 6 ohms resistor is equal to V. V is the same across each branch over this resistor. Okay, this is equal to, you have 15 over 6. You're going to have 2.5 amperes. Now question B, you need the value of resistor R. Okay, so you can still use this formula. Let me show you the same formula to find R. Okay, the same formula to find R. Now to find R, you need to divide by I. Okay, so that you have R. So what you do on the right, you also do it on the left. Now you can cancel. Now you have R alone. So R, the value of resistor R is equal to, okay, you have V over I. Now V is the same, okay? Remember, V is the same across each branch. You need the current through this resistor. Okay, you need the current. We don't have the value of the current through resistor R. We only have on this branch and we have on this branch. We calculated for this branch. Okay, we have it. You also have the total current. This is the total current which is going to split. Okay, it's going to split the total current and then going to join, okay, back to the battery. So this is the total current. So we need to find the current through the resistor R. Okay, so we know that we have V. We need the current through the resistor R. We have the total current. Okay, so the current through the resistor R is equal to total current minus the current on this branch, which is 2.5, minus the current on this branch, which is 3. Now you're going to have the current on this branch is equal to, you're going to have 6 amperes. So you have 6 amperes on this branch and 2.5 on this branch. Okay, 2.5 on this branch. Okay, 2.5. So 2.5 plus 3 plus 6, you are going to have 11.5. Now let's find the value of resistor R using this formula. So this is equal to, we have V over 6. You're going to have 2.5 ohms. Okay, so this is 2.5 ohms. Now question C, determine the equivalent resistance for the circuit. Okay, total resistance. You have a parallel connection, no series connection. So you can use this formula. This is equal to 1 over 6 plus 1 over 5 plus 1 over 2.5. Okay, this is 2.5. 1 over 2.5. 1 over RP is equal to, use your calculator, you're going to have 23 over 30. You need RP, not 1 over RP. You need RP. RP is equal to, you are going to flip. So you are going to have 30 over 23 ohms. You can also calculate the equivalent resistance this way, okay, using the same formula. So RP is equal to this part, okay, this part, remember to raise to the power of -1, okay, so RP is equal to, okay, you have this, okay, to the power of -1. So using the calculator, let's see, you have 1 over 6 plus, okay, plus 1 over 5 plus 1 over 2.5 to the power of -1, okay, to the power of -1. So you're going to have 30 over 23, okay, ohms, okay, can you see? So we are done.